Alright guys, so let's round out the rest of this chapter, which is looking at solutions. So we're going to start out looking at the thermodynamics of solutions, which is actually going to help us explain why some solutes are soluble and while other solutes are insoluble, looking at the different intermolecular forces that are occurring as a solution is formed. We're also going to look at factors that affect solubility besides the thermodynamics behind it, and then we're going to look at colligative properties. So, starting with formation of solutions and the thermodynamics, and remember thermodynamics is dealing with the enthalpy, or heat, or energy of the formation of a solution. So we've talked about intermolecular forces, and we spent a little bit of time on intermolecular forces in this chapter, and we've talked about our stereotypical intermolecular forces, which are our London dispersion forces, our dipole-dipole hydrogen bonds, and our electrostatic forces. Okay, but there is more to it than just that. There are several different types of intermolecular forces that can occur as different types of substances interact with each other. So like when we talk about a dipole-dipole, that is two polar molecules interacting with each other. So that could be water interacting with, let's say, ammonia. Okay, both of those would be polar substances and therefore would interact with each other. Or water interacting with water. Technically a hydrogen bond, but still kind of the same basic principle. A London dispersion force could be two nonpolar things interacting with each other. So let's say we mix chlorine and bromine together. Those interacting with each other would still be London dispersion forces, or just pure bromine reacting with or interacting with bromine. So what happens when we take something and dissolve it in water or in a different solvent? Okay, well, we have three different types of intermolecular forces we're going to look at. First one is called an ion dipole. What does that mean? It's exactly what it sounds like. This is what happens when we take a ionic compound and dissolve it in solution, or dissolve it in water. Remember, a ionic compound is going to dissociate, meaning break down into its ions, and those ions are going to interact with the water molecule. Now, it's very tempting to be like, oh, it's an electrostatic attraction because we have an ion, but it's not technically, because remember, water does not have a pole or an actual legitimate charge like sodium does. It does have the partial negative and the partial positives that are due to the high electronegativity of the oxygen pulling the electrons towards it. But remember, these are not legitimate charges. So with sodium, the interaction between the sodium and the negative, and of course it's positive and negative, the negative side of the water is not actually going to be an electrostatic attraction. It's not like the attraction between sodium and chlorine due to the actual legitimate full-blown charge. This is a little bit different. So we call this an ion dipole interaction. And the reason being is we have our dipole, our negative side, interacting with our positive. There is still an attraction here. It's just not as strong as an electrostatic. So we'll call this an electrostatic one. Okay, we'll just abbreviate that as electro. And then this is called an ion dipole interaction. It's this ion interacting with the negative side of the dipole. Okay, we actually call that solvation, and that's kind of an odd word, but basically what it's meaning is the water molecules surrounding the ions, or technically anything that's dissolved in it. So if we take sodium and chlorine, or sodium chloride and dissolve it, and we have sodium ions floating around, and we have chlorine ions floating around, this interaction of the oxygens interacting with the sodiums and surrounding the sodium ions due to that negative positive interaction. Okay, something like that. And then, of course, our hydrogens interacting with the chlorines due to the positive-negative interaction, because remember, our hydrogens are positive, chlorine being negative. That is called solvation, basically dissolving, if you will. Okay, and that will occur with anything put in water that has those poles on them. Okay, from there, we have ion-induced dipole. Okay, so let's say I take sugar and I dissolve it in water. Okay, sugar is a dipole or polar molecule, and water, of course, is polar as well. That would just be a dipole-dipole interaction. Okay, well, what happens when I take something that's nonpolar, such as ethane here, and dissolve it in with something that is ions or has ions present? Okay, we call that an ion-induced dipole. What that basically means is this guy being nonpolar doesn't have dipoles, but if I put it next to something that has a charge, whether it's a positive or negative, it's going to cause the electrons in this molecule to become unevenly distributed. So if you remember back to when we talked about LDFs, LDFs are kind of like that, the scenario I use as a cafeteria or a lunchroom. And somebody opens up a bag of cookies or a pizza or a cake or whatever, and then people flock to that table. The cafeteria is now unevenly distributed, and therefore there's more people on one side than the other, which is kind of what sort of happens inside a molecule or an atom, except obviously there's no food or logic involved. It just randomly happens where the electrons not all, but more end up on one side than the other, resulting in a temporary dipole, where one side has more electrons and is therefore temporary, partially negative, and the other side has less electrons and is now temporarily partially positive. Well, the same thing's going to happen here is if I put an ion, let's say sodium, next to this molecule, well, that positive charge is going to attract the electrons in this molecule, causing them to shift towards the side where the ion is, resulting in that partial positive. It's an induced dipole due to that positive charge. Okay? Same thing can actually happen if I take something that's polar, not charged, like let's say water, and put it next to something that's nonpolar. I'm still going to get that idea where the poles on the water are going to cause the electrons to become unevenly distributed within the nonpolar molecule. Now this should tell us a little bit about strength involved here. So in technicality, if we're talking about our intermolecular forces, electrostatic is our strongest. Okay? And that is because it's got legitimate charges actually attracting to each other. Okay? From there, that ion dipole would actually be kind of our next strongest, and that's because, again, that charge interacting with our dipole. Hydrogen bonds would fall somewhere in here as well. Then, of course, we'd have our dipole-dipole. Okay. We would have our ion-induced dipole. And in reality, these two could be switched. And the reason I'm saying could be is because it does depend a lot on the size and charge of the ion. These two could probably flip back and forth, and even hydrogen bonds might flip back and forth. So these three, in terms of actual positioning, could vary. And again, that reasoning is going to be based off the size of the particles that are interacting with each other. So what I'm referring to here again is Coulomb's law. Okay? And Coulomb's law is going to play a big role in terms of how strong these forces actually are. But we'll just kind of put them like this for right now. Okay? From there, we would have the dipole-induced dipole. And I'm just going to abbreviate induced like that. Okay, and of course then we have our LDFs being our weakest ones, which would be our two nonpolar things kind of mixing. So that kind of gives us a grand scheme of strength. So electrostatic is our highest. Anything dealing with ions are typically pretty strong, so they're up here. So again, this ion dipole can flip back and forth here just depending on how big the ion is and its charge. We have hydrogen bonds and dipole bonds. Dipole-dipole interactions fall into this range as well. Dipole-induced dipole, and then of course our LDFs, just to kind of give you an idea of strength and kind of getting a basic idea of where these are. Okay, and again, these all vary based off of Coulomb's law. This is just a general idea. Okay, from there, let's talk about solutions. When we're making solutions, there are 3 steps that occur. Okay, and this is kind of odd to think about because it's all happening simultaneously or kind of all at once. It's not like it's actually happening in steps, but it also kind of is in terms of the thermodynamics behind it, meaning we're never actually going to see these steps, but this is what we hypothesize or theorize is going on. The first thing is the solute separates into individual components. So what in the world does that mean? Well, let's take sodium chloride, for example. That's a solute. I put into solution, it's going to separate into its components, which means it's going to separate into sodium ions and chlorine ions. It's going to ionize, okay? Or let's say I add sugar into the mix. Well, these sugar molecules are all interacting with each other, so separating those sugar molecules into individual molecules versus the compound all mixed together, the compounds all mixed together and bonded together are interacting with each other. It's separating into individual sugar molecules, okay? The next thing is the solvent then has to separate, and what it's doing is it's expanding to allow for the solute to mix in, okay? Which means I have 2 waters interacting with each other. we have to separate those waters. Well, we don't have to separate those waters. They separate themselves to allow for the interaction with our solute. Okay, and then the last step is a solute and solvent interacting. So now we have our sodium ion interacting with our water molecule. Okay, and our chlorine ion interacting with our water molecule, our sugar interacting with our water molecule, however we want to think about it. Okay, so these are kind of the basic steps. So the first thing is we separate the solute, we separate the solvent, and then the solute and solvent interact with each other. Now again, what we're looking at is the thermodynamics of this. So let's kind of think about what's going on here. In step 1, we are separating the intermolecular forces between two components. Well, if we remember back, breaking intermolecular bonds or breaking any bonds is an endothermic process. It requires energy. Okay, same with step 2. We're separating the solvent. We're breaking the solvent into individual components. Again, same idea. We're breaking intermolecular forces, requires energy, endothermic. Okay, step 3 is allowing for the intermolecular forces between the solute and solvent to interact with each other. Well, that is forming intermolecular forces, which is a exothermic process. Okay, so we kind of get this idea of separating is endothermic and combining is exothermic. Okay, and that's going to play a role in understanding the thermodynamics behind our reactions. Okay, or behind our formation of solutions. So just to kind of give you a picture, again, step 1 is separating our solute. Step 2 is separating our solvent, and it really doesn't matter which one of these is first. Okay, you're separating both of them, one step 1, one step 2. And step 3 is the combination of the two together. So again, requires energy for step 1, requires energy for step 2, and releases energy for step 3. So positive, positive, and negative. And let's talk about that positive and negative, because I don't think that's something we've really discussed. Endothermic means it's requiring energy. And when we talk about thermodynamics and we talk about enthalpy, we are always looking in terms of the system. So if it's endothermic and it requires energy, that means the system gained energy. Okay, so those will always be a positive delta H. Okay, endothermic is always positive. Exothermic means it releases energy, which means the system loses energy. Therefore, exothermic will be a negative delta H. Okay, so step 1 will be positive, step 2 will be positive, step 3 will be negative. And again, that's because endothermic, endothermic, exothermic. Okay, we're going to stop there, and on the next video, we're going to actually look at what's going on with these 3 steps and use those to determine whether a solution will actually form. In other words, if the solute is actually soluble or not, based off of just this information alone. Okay, thanks guys.